Hello everyone. I believe that we all are aware of the recent expansion of AI and what's called large language models. Today we'll explore how machines break down text into digestible units by the process called tokenization, which is the first step in NLP pipeline. Before we start the lecture, I expect that all attendees have at least introductory knowledge within the following concepts: Python, mainly dealing with string manipulation, text, data structure and regular expression, data concepts, knowledge of raw and structured data, and the concept of vocabulary, mathematical foundation, including linear algebra, vectors and matrices, and basic probability knowledge for basic tokenization algorithms. So let's start by thinking about the term tokenization. What is tokenization? Tokenization, in simple words, it's the process of splitting text into smaller units, what we call tokens. And a token is a unit of text. It might be a word, subword, or even a single character. In fact, tokenization is not limited to the text data. We have the text data, we have the audio and speech data, and where we took the tokenization transforms waveform into acoustic frames or learned discrete units. Also, we have tokenization for image and vision models, in which we split the image into batches or regions, and then we handle it as tokens. We have also the multimodal AI, which handles or apply different modalities to handle text, image, and audio. Then we tokenize them separately, but at the end we need to align them in a shared embedding space. Tokenization also included in data security, where we transform or convert sensitive data like credit card numbers, personal information details, into non-sensitive representative tokens, and we utilize mapping table in order to go back and forth, for example, to tokenize this term into the original data. So just I want to visualize how the text is fed into the model. Let's say that we have this paragraph and we want to tokenize it. We apply a tokenization algorithm in which each term is separated and handle it as an independent token. I want you to focus on the spaces that which is represented by underscores here, just to understand that this term is the full term. So we don't have part of the term from that's connected to different characters or set of characters. While when we start with the line, for example, a, to, and but and was, you can see that we don't have the white space here, because here we have a new line which has kind of different treatment with the tokenization. This tokenization was applied by using the 200K base model with fast BPE open source tokenizer from OpenAI. So the large language model or the AI model, it should handle not the text itself, but the IDs that's behind the, so we need in the tokenization, we need to extract the text, tokenize the text, and then use the ID of each tokenized token from this tokenized text in order to feed the data into the model. So now let's think about the tokenization method. We have different tokenization method. Some of them handle on the character level, in which each character is a token. It was applied in early NLP and some multilingual models. Here's an example. I learn NLP. You can see that we handle each character as an independent token. And the vocabulary will be the characters. The word level, we split the text into spaces, punctuation, or regular expressions, which applied, generally speaking, in classical NLP and early word-to-vec model. For example, I learn NLP, you can split it into 3 different tokens by white space. The subwords is a different method which was introduced recently in the last decade. And we listed the most four methods of the successful methods of the Subword, which started by BPE, in which we iteratively merge frequent character pairs until we build the vocabulary, and there is a threshold that we need to stop it, whether it's the size of vocabulary or the training data is ended. We have and it was introduced by Sennrich et al. In 2015, and it's widely used by GPT. We have the WordPiece, which proposed by Schuster and Nakajima in 2012. Actually, it learns subwords maximizing likelihood of training data. So it computed the tokenization algorithm, or the tokens, by computing the subwords that maximize the likelihood of the training data. We have also the Unigram LM, which was introduced by Kudo in 2018. Actually, it selects subwords from probabilistic vocabulary. So we have the vocabulary, and we need to extract the tokens from the training data by minimizing the loss by applying this vocabulary in the training data. We also have the Byte-level BPE, which is similar to BPE. However, it combined the byte form, so it's byte level. It's not the character level, and it enables full Unicode coverage. So you can see that, and it's applied in GPT-2, GPT-3, Llama, DeepSeek, and actually even in GPT-4 there's kind of hybrid mode, but mainly it's from byte level BPE. That's why you can see that it handles emojis very well. So let's take an example just to understand what's going on behind the scene. Let's say that we have the training data, which is a sailor went to CCC. It's the whole data that we are going to train our tokenizer to segment the word during the inference mode. So initially we extract the symbols, which are the characters. I want to emphasize you to pay attention to the characters where we have white space before that character. For example, underscore S, it means white space before S, while when we don't have underscore, it means that this character was connected to the character or the token that's behind it. The initial vocabulary that we have is the characters, including, of course, the characters with white space. We check what are the most frequent pairs in the initial symbols. We notice that the underscore S with E is the most frequent, so we merge it. We use this term to update the symbols and to update the vocabulary. So you can see that we added it to the vocabulary, and we converted the S followed by E into one token or symbol. So the most frequent pairs now is underscore S with E, which is a space SE followed by A. So we will merge it to form the term C. So you can see that now the next symbol we have it CCC, and we have the vocabulary extended to include the S, the C, the word C. Now we found that space S followed by A in the sailor word, so we merge it, and we keep continuing until we reach to the point that we have the final symbols, which is the training data, with the final vocabulary that we built during the process of building the tokenizer. So the final active tokens is the set of words that included in the example. Now let's think about how to the model will handle this token during the inference. The tokenizer will go, so let's take the sentence which is to see what he could see. It's clear that we have some characters and some words that are not in the training data. Can you guess what is it? I will give you just 5 seconds. Okay, so you can see that we have 2, it's available. We have the first 2 characters of C, because we have the term C. We handle it and we keep E as an independent, but however we have in the vocabulary the term E. We have the character W that follows a space. However, we don't have the term H, so it's replaced by unknown. We have A, we have T, but we don't have H, so it's unknown. And we can keep going whenever we see or experience a new out of vocabulary term or token. We can add it to the sentence, to the model. So by asking the model to regenerate the term, we can see that it will say the following term: to C, W, unknown, at, unknown, E, unknown, O, unknown, I, unknown, C. This will give you a hint about the importance of having a training data set that is very helpful to have a fully knowledgeable tokenizer. So to wrap up, here are the key challenges in tokenization with large language models. The first one is finite vocabulary, and we might experience out of vocabulary tokens. So it might be possible to decompose it, like what we did with that character E and H and E from the term he. For example, if we saw a metaversal, which is a new term, then we can decompose it to meta and versal, or treat it as unseen token and replace it with unknown, like what we have done in the some characters in the previous example. Ambiguity in subword segmentation, especially when we utilize different tokenization algorithms. For example, whenever we are utilizing the model that interact with a different model, and both of them utilize different tokenization algorithms. Tokenization bias. Frequent or dominant language patterns are overrepresented in the vocabulary, which will affect the lower resources languages or dialects. Also, loss of semantic boundaries. For example, breaking words into subwords can distort the meaning. For example, especially in the morphological rich or compound language like the German or Turkish. For example, we have the term Evleriniziden, which means from your houses. If we split them, then we will have a new different tokens. So it might be mapped differently from the required or the original meaning. Context insensitive tokenization. Most tokenizers segment text without considering the context. For example, the term lead, if it is the noun or verb. Inefficient representation of long or rare words. The rare morphological complex words can explode into multiple tokens, which will increase the length and computational cost, and the domain adaptation. The takeaways from this lecture: I want you to focus on understanding that the tokenization is a foundational NLP, foundational process in NLP. Supports methods balance vocabulary size and coverage. Never reinvent the wheel. Utilize the available libraries, unless you are handling a specific domain. To use a fine-tune LLM, or to use and fine-tune an LLM, have full awareness of its tokenizer, especially at specific domain utilization. Tokenization relies on predefined vocabulary. Finally, tokenization is the bridge between raw text and numerical inputs, the token ID with which the model will handle. Here are the extra readings that I prefer you to read. Some of them are referenced during the lecture. I highly recommend reading the chapter 12 from the Understanding Deep Learning book, and I provide you with fully documented notebook that you can utilize to practice after the lecture. Thank you very much.